Today we already had 2 sessions, quantum sensing, atomic gravimeters and gradiometers with Nicole Metche. Then the quantum key distribution, everyone got a thorough introduction today by Aisha Khalik. And soon, JIBRAN, the floor is yours to continue with QBronze and QNickel, quantum computing and programming. Tomorrow we will start again with the quantum sensing topic. Really interesting. How can quantum sensors be used to image the brain? Quantum sensors, magnetometers based on atomic vapor cells, they can be used to sense magnetic fields that are 1 billion times smaller than that of the Earth. And this can be used to image magnetic fields that are induced by currents in the brain. And tomorrow, Svenja Knappe will tell us about the concept, the physical concept, and really the applications in the biomedical field. And then we will continue our workshop series with QKD and quantum computing and programming. Now, really, the floor is yours, JIBRAN. Please go ahead.
I would love to have, hopefully by next year, a quantum workshop on quantum sensing as well. So fingers crossed on that.
Oh, great. I think we could do a full week or even a month on it. There is the field is so promising. And many startups popping up right now all over the world, very near-term applications.
Exactly.
And one atomic clock, that is the oldest quantum sensor, and it has been setting the standards for more than 50 years all over the world.
Exactly, right, true. Yeah, so I'm definitely joining tomorrow's talk. All right, hello everyone, welcome back. It's good that I did not scare you away, I hope, yesterday with the condensed version of Intro to Quantum. As mentioned again, yesterday, please be dissuaded by the quick pace of the session yesterday. There's a longer version of the same talk, in fact, versions. There are 3 talks that were condensed yesterday into one. So you can go to Canvas and go through the 3 different talks at your leisure to really make sure you understand what was involved. Today's talk, we have more time as well, and we have a different content. We have some content from Nickel that we'll start today as well, so it should be slower as well. There is some content from Bronze in the beginning. So the idea is we've got our introduction from classical and quantum information from yesterday. We kind of stopped right at the definition of an entangled state. So that's what I'll start from today. We'll go into a little bit of discussion of what does it mean for a state to be entangled, and then move on to some basic quantum protocols. You've already seen a nice discussion of one of the key applications of introductory quantum protocols, i.e. quantum key distribution. We'll do a simpler version of 2 other protocols, and then we'll move into kind of a computer science crash course. If yesterday was a quantum crash course, today is going to be kind of a theoretical computer science crash course in complexity theory. And the reason why I've kind of added it is, so hopefully when we do kind of quantum algorithms starting tomorrow, and then application of Grover's algorithm to max cut, we approach the discussion kind of in a more quote unquote sophisticated fashion, in the sense that we're able to understand what do we mean when we say a certain problem is NP hard, NP complete, and so on and so forth. So today my goal will be to ensure that everyone that's participating in the session can understand the distinction between these different complexity classes that are coming in from computer science. As again, please put your questions on Discord, and hopefully I'll take them as they come. Right, so as we mentioned yesterday as well, day 2, we are going to be talking about this part of the quantum bronze or QBronze workshop, and in addition, the complexity theory bit that I just mentioned. Right, so yesterday we had finished at the definition of this entangled state, a Bell state. Recall in ket notation, you could also write it as just 1 over square root 2, 0, 0 plus 1, 1. But I'd like to just kind of pause over here and note the similarity between something that's quintessentially kind of quantum entanglement, and note what the classical counterpart kind of looks like. They're very, very similar. It's, you know, you don't even have the minus sign. It's just missing a square root. When you think about it, this is kind of like a correlated 2 bits that are correlated, right? So with probability half, they'll be 0, 0. With probability half, they'll be 1, 1. And that's exactly what you have over here as well. if you think about measuring this. And so I emphasize this in kind of last year's session. I'll emphasize this again just because I like this kind of observation. Lots of times in popular discussions of quantum information of introduction to entanglement, you'll see kind of discussion of this Bell state and say something along the lines of, hey, so you have two qubits over here, right? And the idea is Alice, Bob, insert your famous or favorite characters if you don't like Alice and Bob. So Alice has one qubit, Bob has second qubit. I'll just keep repeating Alice and Bob because that's what I'm used to. So Alice takes qubit 1, Bob takes qubit 2, and head off. And the popular science discussion really says, if they're entangled qubits, then they'll have this wonderful consequence that as soon as Alice measures a qubit and finds that it's in the state 0, she will instantly know that Bob's state is also, Bob's qubit is also in the state 0, and vice versa. If she finds 1, then she knows that Bob's state is also 1. And what I'll just want to note here is that there is absolutely nothing in that explanation that requires quantum, right? So this is something that can be said of completely correlated classical bits as well. The usual standard example would be, imagine the classical preparation procedure involves preparing 2 envelopes, which will, let's say, contain either red paper or green paper. Alice and Bob don't know which ones I'll prepare. I flip a coin. If it comes up heads, I put 2 red papers in each of the 2 envelopes. If it comes up tails, I put 2 green papers in the envelopes, and sealed envelopes, give them off to both of them. They head off, open the envelopes, and exactly the same kind of structure happens. Alice knows that Alice gets a red paper. She knows Bob has a red paper, and vice versa. So that notion is just the notion of perfect correlation. There's nothing entangled about it. There is a subtle distinction in terms of our intuition of when the value of this physical state or the color of the paper is getting fixed. In the classical experiment, our intuition suggests, obviously, that as soon as I've sealed the envelope, the color of the paper inside the envelope is fixed. And quantum mechanically, though, that's intuition actually breaks down. It doesn't really work without necessarily going into the details. Quantum mechanically, we're led into thinking that the state or the color of the paper, if it were a quantum paper, gets actually determined at the time of measurement rather at the time of preparation. So that's a subtle distinction that's crucial, that plays its part in quantum key distribution protocols as well. And maybe we can discuss that more on this call. All right, so if you take away nothing from this discussion apart from being able to realize when a popular science discussion is not good, I'm happy with that. All right, with that, let's move on to 2 pioneering quantum protocols that identify this idea that quantum information protocols can really do something that is not possible classically. The first one is known as superdense coding, as we'll see soon why. Word about the figure, the representation. The idea is time is moving left to right. It's a circuit. This dotted line represents kind of a physical separation between our 2 favorite parties, Alice and Bob. The 2 parallel lines represent flow of classical information. The single line represents flow or evolution of quantum information. And these then are logical gates that are being applied. This from yesterday is the control NOT gate. This then is the control Z gate. So this is the control bit, and the side with a -1 on it is where the Z gate is applied, conditioned on the control bit, right? So just like this is a control X or control NOT, this is a control Z. This line flows through this separation. So that means that there's a quantum bit that's being communicated from Alice to Bob. Once Bob receives it, Bob also performs certain operations on his side of the qubit. And just reading the labeling on the circuit, you see kind of what's happening. Alice starts out with 2 classical bits of information, A and B. Yes, exactly, they're classical bits, Ron. Does some logical processing on her side. She had a quantum bit that's entangled with Bob's quantum bit as well. In fact, it's exactly the Bell state that we had been working with in the previous slide. So Alice has 2 classical bits plus a qubit that's shared with Bob's qubit in the maximally entangled state, 5+. So that's what we'll usually label 0, 0 plus 1, 1 state as. After this logical processing, Alice sends her share of the qubit to Bob. So Bob has both the qubits now. performs these two operations, and this figure is claiming that, hey, Bob now on his end will receive A and B. The states that he has now will be in the state A and B. Note what's happened. The entanglement that they started out with is gone now, because Alice actually doesn't even have the quantum state anymore. But it's also the case that Bob's two states are no longer entangled. In fact, they're exactly in the two classical bit states that Alice started out with. Hence, perhaps not that surprisingly, via the communication of one quantum bit from Alice to Bob, Alice has been able to communicate two classical bits to Bob. So that's why it's kind of called super dense, that she's been able to concentrate or compress two classical bits of information in one quantum bit, right? There is something known as a Halevo bound that we won't be able to get into these in this workshop, which says that if you expect this to be improved, i.e. send 3 bits via one quantum bit, then such possibilities are not going to work out. This is optimal, i.e. via the transmission of one quantum bit. At best, you can hope to achieve transmission of 2 classical bits. All right. Let's quickly work through one example, and then we'll fill in the remaining. So as suggested previously, we'll cut off this circuit into kind of time slices and then work our way forward. So the starting state at time t0 we already know. We'll just write out the quantum state. The quantum state is 5+. So let's assume A and B have the value 0, 0. Well, in this case, the control operations are not going to occur, right? Because the control bits, both A and B, are 0. Hence, the state over here will be 5+, i.e. the joint. So we'll write down the joint entangled state between Alice and Bob after execution of control Z, which essentially doesn't get implemented because A is 0. Similarly, B is 0. So state at time t2 also remains same. So 5+ remains 5+, right? Next, the bits, the quantum bit is communicated from Alice to Bob. There's nothing that changes in the representation of the state because of that. However, now a C0 gets applied with the first qubit as control. So the first qubit is control, the second qubit will get flipped if the first qubit is 1. So naturally, nothing will change over here, but this will change from 1, 1 to 1, 0. So this state you can write now as 1 over square root 2, 0, 0 plus 1, 0. You note now that the second qubit is always in the 0 state. So you've taken your entangled state, which could not have been decomposed into a tensor product structure at this point. But now, after applying the C0, this can be written as 1 over square root 2, 0 plus 1 as the state of the first qubit, tensor just a 0, right? Because the second qubit is always in the state 0. And then this thing is just a plus state. So this is essentially just a plus state and then 0, right? And you recall from yesterday, Hadamard applied to 0 equals plus, and Hadamard applied to 1 is the minus state. And so over here, state at time t4, you just get a 0, 0, because Hadamard got applied to the 0 plus 1 or the plus state. So great, we verify that if AB was 0, 0, there's 2 states that Bob is left with at the end of the protocol are indeed 0, 0. And in fact, you can go through exactly similar calculation. It's easy to verify the calculation right here. You'll be able to see the slides that in all the remaining 3 cases as well, Bob eventually ends up with exactly the state that Alice starts out with, the 2 values of A and B. The -1 sign over here, the minus sign over here shouldn't really cause an issue, because recall, this is essentially just a -1 in front. When you take the square, that will just become probability 1. And so the minus sign doesn't really cause an issue for us over here. That's the distinction between a global phase versus a local phase. There's more discussion about that in the workshop notebooks. So this kind of verification via brute force calculation verifies for us that the super dense coding protocol achieves exactly what we claimed by sending, transmitting 2 classical bits of information via 1 quantum bit. Questions? Someone's typing. All right. So let's do it the other way around, kind of almost, which is perhaps more interesting. It's known as also the quantum teleportation protocol. In the quantum teleportation protocol, we've got a similar setup. Alice and Bob, two parties spatially separated. They share an entangled state. But now the starting setup is kind of reversed. Alice, rather than having two classical bits to transmit, has a quantum state. And the interesting thing here is you can assume that's it. It's an unknown quantum state. Question about the previous slide. T3 to T4, how is it done? Recall at T3, this is what we were left with. Then going from T3 to T4, the first qubit got the Hadamard applied on it. And we know that Hadamard applied to 1 gives us a minus state. Recall from yesterday, Hadamard is self-inverse, so apply Hadamard again to the minus state, you'll get 1. If you apply Hadamard to the 0 state, you get plus. If you apply Hadamard again to the plus state, you get 0. So Hadamard applied to the plus state gave us 0, and so you got your 0, 0 back, right? All right, quantum teleportation. The sound is definitely nice. In fact, historically, that's how kind of IBM kind of sold it as well. They ran an ad in, I think, in Scientific American about someone teleporting some goulash to someone or whatnot. I think you should be able to look that up on Google, but it was kind of hard last time I tried. Anyhow, so what's the idea over here? It's not the quantum teleportation from X-Men or Star Trek. Why? Because if you recall the teleportation in Star Trek, the idea is you've reached an unknown or new planet, and without ever having actually physically visited that planet before, in Star Trek teleportation, you can choose to kind of teleport your mass from Starship Enterprise to the surface of the planet, let's say. In quantum teleportation, as we'll see, you need to have kind of a prior arrangement beforehand between kind of the two spatial locations between which you are planning this transmission of information, right? So if you think about them as the locations where Alice and Bob are located in the labs, they need to have this prior entanglement shade between them, right? So there needs to be a 5+ shade between them. Then what the quantum teleportation protocol is achieving is that if Alice has an unknown quantum state psi, Alice doesn't actually need to know the values of these amplitudes alpha, beta. Alice is just given a black box with a quantum state in it. If she's able to apply these transformations to them, to her states, so she's got 2 qubits now, right? The state she was given and the qubit that she shares with Bob in the maximally entangled state or the jointly entangled state. So she performs these 2 operations and then measures her 2 qubits. This will result in 2 classical bits being generated, kind of like she had 2 classical bits to send in the superdense coding case. These 2 classical bits are now communicated to Bob. Note, again, the entanglement now at this point is destroyed. Once she's measured over here, she's obtained 2 classical bits, hence the entanglement over here between Alice and Bob is gone. But now Bob receives these 2 classical bits, performs a bunch of post-processing on his side, and the claim is that Bob is now able to receive psi exactly, assuming all operations will perform perfectly, as Alice received. So Alice, without ever knowing the state psi, is able to have Bob receive the state psi. And interestingly enough, if it were the case that psi was actually entangled with some other party, Charlie, then once Bob receives that state psi, then this psi will actually still be entangled with Charlie's state. So entanglement is preserved for the state psi, even though the way I've represented over here as in introductory discussions is just kind of a single qubit that's not entangled with anything else. So let's work through the evolution of this circuit. Right. All right. So our qubits on Alice Bob's side are the state psi that needs to be teleported, and the maximum entangled state 5+ between Alice and Bob. So that's your initial state. We just expand it out over here, and then we combine them together to write it as such, right? So all the 3 qubits are now written together with their corresponding amplitudes, right? So monogamy of entanglement is preserved, right? So we are not, so it's not as if Alice already had, Alice doesn't continue to have any state, a quantum state any longer, right? It's the state that Alice had now being received by Bob, and it's Bob's state now. It will be entangled with whatever Charlie had. So there's no issue of monogamy of entanglement. You're not creating new entanglement per se. You're just saying, hey, in some sense, the state psi that was entangled between Alice and Charlie is now entangled between Bob and Charlie. Right? The entanglement with Alice is gone, and it's now rather entangled with Bob's quantum state. Okay. So this is the state at time step 1. You apply C naught on the first 2 qubits with the first qubit as control. It's easy to read off. Well, there's 0, 0 over here, so nothing will change. The first qubit is 1 over here. So you get a flip over here of the second qubit, which you can verify. Here it was 0, zoom in, it became a 1. Here it was 1, it became a 0. Right? Now, Hadamard again gets applied on the first qubit. You get kind of an expansion, which leads to a longer state. I'll let you verify that indeed this is what you get when you get this expanded state out. So there's a longer question. All right, so we're talking about entanglement quantification. I'll take that up on Discord later on directly. So we applied Hadamard, resulting in this long state. And now what we have done is taken this long state representation and collected terms of the first 2 qubits. Why are we collecting these terms? Well, because we know Alice now needs to measure or will measure the first 2 qubits. So it's nice to be able to collect those 2 qubits together so we can directly kind of read off, well, if Alice has 0, 0, then this is what Bob has, and so on and so forth. If Alice has 0, 1, then this is what Bob has, and so on and so forth. Right, so we have exactly the state. And now let's just work in kind of a piecewise scenario. Let's say Alice performs this measurement, gets 0, 0. Well, in that case, the qubit that is remaining with Bob has this representation. Well, that's exactly what Alice started out with. The 2 bits, classical bits that Alice will send to Bob will have 0, 0 value in this case. So neither of these 2 control gates will be applied. And so Bob has exactly the state psi. However, if Alice measurement results give 0, 1, then Bob's state is alpha 1 plus beta 0. You get the bit 0, 1 sent over here. So the control naught will get applied, not the control Z. When you apply the control naught, this alpha 1 will become alpha 0, and this will become a beta 1. And so even in the case when Alice has 0, 1, as a measurement result, Bob indeed does receive psi. And you can verify exactly the same kind of almost error correction procedures happening in the remaining 2 cases as well, such that it guarantees that Bob, in all the 4 cases, receives exactly the state psi. And so that's what's referred to as quantum teleportation. Interestingly enough, it's kind of nicer in some sense that superdense scoring, right? Because Alice didn't know the values of alpha and beta. And so these alpha and betas could be arbitrary kind of long, could have arbitrary long representations, right? And assuming this circuit can be implemented perfectly without any noise, this is claiming that exactly that psi with that exact same alpha and beta gets created on Bob's end. And so there's kind of something much more subtle in terms of the transmission that's happening over here via this pairing of 2 classical bits transmitted and 1 pair of shared entanglement state. When entanglement is preserved, so what I meant with entanglement is preserved was the notion that if this state psi was not just the state alpha 0 plus beta 1, but rather was something like this phi plus, that is, this psi was entangled with another state that Charlie had, so naturally this would have separate representation. You take that state and now perform exactly this circuit. The state that Bob will receive on this end will now be entangled with what Charlie had. So that entanglement is preserved. That entangled state that Alice had with Charlie is now entangled with the state that Bob had. So that entanglement between the 2 states is preserved. Right. Osman, your question is rather long, so I'll read it right after the session ends. Why did Alice measure only first 2 qubits? Well, because Alice, in this case, Alice only has 2 qubits. right? So it was in the superdense scoring where Alice had 2 classical bits and 1 quantum bit. In the quantum teleportation case, Alice just has 2 quantum bits. So those are the 2 qubits you can measure. Right? Can we distinguish between the state that Alice had and the one that Bob has later? So I'm not sure in what sense do you mean distinguish? Because, well, if you kind of did some kind of tomography or prepare identification procedure over here, you're already kind of destroying the state such that you won't be able to reproduce it on Bob's end. Mathematically, in terms of the presentation of the circuit, you do kind of get this verification that, hey, if the entire circuit is implemented without any error, then indeed what Alice started out with is what Bob got left with. Right. The preserved entanglement. So Valerie, I would kind of say that I would say that quantum teleportation protocol preserves entanglement. So via the teleportation procedure, whatever the state that we are teleporting, if it was entangled with something, the teleported state continues to be entangled with that state. Exactly. So whenever you see this measurement happening, you know that the quantum state superposition, entanglement, or whatever it is, potentially is getting destroyed, right? And that's signified here more explicitly by the fact that the measurement is resulting in kind of these 2 parallel lines. So we know that 2 classical bits are being forwarded. So rather than the table, you can think of this kind of 4 expressions over here as the 4 different cases, right? So in the case of 0, 0, the evaluation is right there in this expression that when the measurement result was 0, 0, the teleported state is, or the state that Bob has, is exactly with the representation that Alice started out with. In the case where Alice gets 0, 1, then alpha 1 plus beta 0 is the state that Bob receives or Bob has prior to these 2 procedures. We note that since A is 0, B is 1, yeah. So the first measurement bit controls the Z, the second measurement controls the C0. So that's why you're applying the X operation on Bob's qubit here, which results in this flip. So this is the 0, 1 case. Maybe I'll just identify it for clarity. So this is the 0, 1 case. This is the 1, 0 case, and this is the 1, 1 case. All right. Okay. So these are 2 of the pioneering quantum information protocols. There's lots that's been said about them in the literature and built upon. We don't have the time to do it. If just to get started, you look at the 2 circuits and you obviously see there's a nice kind of symmetry going on between these 2 circuits, and you are welcome to kind of read about it more and see what's involved. But that's it for kind of these introductory protocols for now. We'll start building towards this foundational steps for quantum algorithms. And the first step towards building quantum algorithms is to make sure that we can do everything that you can do quantum in a classical computation. And the first time you hear that, I'll repeat that. We want to ensure that you can do everything in quantum computation that you can do in classical computation. That perhaps might seem obvious if you haven't thought about it first, because you're like, hey, isn't quantum computation a superset of classical computing? Yes, it is indeed. But then there are subtleties. In what way? Well, quantum mechanically, they've identified the fact that all transformations, i.e. evolutions over time, are going to be unitary or reversible operations. Classically, we don't necessarily have that restriction when we think about applying logical operations. Case in point, think about how in a standard kind of logical circuit you think about applying the AND gate. Let's see, operate on states doesn't destroy the superposition. All right, so just a quick pause. Samantha has this question about touch upon why operating on states doesn't destroy the superposition. So you just do the math in order for this verification, right? So distinguish between, first of all, applying a unitary operation versus applying a measurement. If you're applying a unitary operation, they are in fact procedures through which we can create superpositions, right? Whereas when you apply a measurement, that's when you're, based on our kind of formulation so far, we are projecting the state into one of the potential basis states that we have prepared our state, the space in which we have prepared our state. So it's the measurement procedure that's quote unquote going to project our state into one of the basis states. But if you're looking to create superposition, then we've seen the standard example like Hadamard applied to 0 gives us superposition by giving us 1 over square root of 0 plus 1. Indeed, it kind of takes away the superposition as well. If you apply Hadamard to the plus state, which is exactly this state, then your superposition kind of goes away and you get the 0 state back. So it really depends on the state that you have and the operation that you're performing that results in what you get, whether it is in superposition or not. This is a slightly naive kind of statement, but I think it's enough for our current applications. Okay. So there's discussion going on about quantum non-locality and stuff. I'll contribute to that later on, hopefully. Let's get to kind of transformations now. So that we are forming the building blocks of how we want to think about quantum algorithms and quantum circuits. We've seen some almost toy examples, if you want to call quantum teleportation a toy example, but we want to be able to now talk about general algorithms, hopefully by tomorrow. And towards doing that, we want to be able to say, hey, how do I do anything that I can do in a classical circuit? The first thing that we have got to overcome is this notion that all quantum transformations are reversible. But when I apply an AND gate in a standard representation in a classical circuit, it's not a reversible transformation, right? If I know the value of this AND gate, I can't reconstruct what the input values were. If AND is 1, then yes, I know both the bits were 1, 1 input bits. But if AND is 0, then I don't know which of the 3 input possibilities occurred. How do I overcome that? Well, I could potentially add another output bit in my classical bit, but then what value should this take? I do want the AND value itself. Should this be the X value or should this be the Y value? I still miss a bit of information. And so one standard representation of thinking about this, and this is now completely classical, right? So classically, we can also implement all logical transformations in a reversible manner. I'm not an expert in the history, but from what the brief reading I've done is that when the initial digital logic and circuit design were being developed, part of the proposals were in fact to implement all transformations in a reversible manner. You can kind of see the benefit of that as well, because it's a reversible transformation. You're kind of, in principle, implementing it in a without any loss of information fashion. So the nice kind of outcome, or well, nice in a way, in a bad way. The reason why your laptop on your lap today, on the phone that you're holding, or the device that you're computing on is heating up, because all the circuitry is performing computation in this irreversible way. Information is coming in, some of that information is lost in the output. Where is that information going? Well, part of that is the heat that comes out of your computational device. And if you implement it in that reversible fashion, then at least that information is not getting lost. So since all transformations in the quantum case need to be reversible, we have the structure that will impose that any classical computation that you have, if you were thinking about it in this way, we will now think about it in this way, where you have all your original input preserved in the output, hence your transformation is reversible, and you have an additional amount of memory, depending on whatever is the amount of storage you need for your output, that will actually start and be initialized, let's say in the 0 state or a known state, and you will have the value of the function you wanted to compute, whatever logical gate you wanted to have over here. In this simple example, it's the AND gate. It could have been something else as well. That additional value of the function will be computed into this additional storage. Hence, in this way, it's easy to convince yourself you can apply any function, or you can implement any logical circuit in a reversible manner. And so this is the way we'll think about classical gates implement as unitaries. So the idea is this A perhaps is not just a single qubit, it's a sequence, it's n qubits combined together in some state A. This B is your additional bit, and let's think this unitary gate B sub f is the encoding as a unitary of this Boolean function f that maps n bits to a single bit. So these A then represents the input in terms of n qubits, encoded in n qubits. This B is the single additional bit, and after implementation of B sub f, you will have the function f evaluated on the input A, XORed into whatever was the value B. And you can easily convince yourself that this is going to be reversible, because if you just imagine applying another B sub f over here, well, you'll just have another parity of f of a come in over here. Well, f of a parity f of a will equal 0, and so you'll get exactly what you started out with in the output case as well, in the additional bit, which will be just B. So this is our standard dictionary for applying any classical gate, that you have this additional memory, additional storage, and you will XOR your result into it. For many of our quantum algorithms, we'll think of them as an oracle. We don't always have to think of it as an oracle, but here in many quantum algorithms, we'll think of it as an oracle that's implementing some function f. All right. Using this representation, we'll implement a nice trick called phase kickback, which is really just a little bit of playing around with the math of what we just defined. So here, when I gave this representation to you, we kind of didn't think about the superposition, right? What is the parity? Parity is just the XOR logical function. So if you've got A and, well, A and B is not a nice choice on this page. Let's choose X and Y. If you've got X and Y, then parity of XY is just 1 when exactly one of the input bits is 1, right? Or in other words, it's counting even or odd number of ones on the input. So in these two cases, I value it to 1. In the other two cases, I value it to 0. Right, so that's the logical XOR parity. Okay, so what's the phase kickback trick? Note that in the previous example or definition, we had fixed B to be, let's say, some value 0 or 1. But now when you're talking about quantum information, this state doesn't necessarily need to be in 0 or 1 state. I could choose to define it to be in some other state. In this specific case for phase kickback, I define it to be, let's say, in the minus state. And that's easily doable, right? So you start, if this was initially B, B was equal to 0, you just apply first the X state to make it 1, then you apply Hadamard to make it the minus state. And so you can easily get the minus state being fed in over here. Well, how will this B sub f work out based on this definition? It follows similarly by definition that, well, B sub f applied to A minus, well, let's expand out the minus thing. It becomes this. Let's just apply bilinearity. B sub f of A tends to 0, B sub of A tends to 1. In these two cases, I can apply directly the definition over here. So here it will be 0 parity f of A, the 0 from here. A was the input, so f of A. Same over here, 1 parity f of A. So you get this longer expression. So far, the way we've been doing it, it seems like pretty much by definition that the output is being computed into this additional storage bit. The phase kickback is a nice trick where we now observe that, well, if f of A is 0, so I'm just doing conditional reasoning. If this f of A was 0, then this expression over here simplifies to exactly this, right? So imagine that A has been taken out as a common factor. F of A is 0, so this will be 0 parity 0. So this simplifies to 0. 1 parity 0 will be 1. So you'll get 0 minus 1 as the value of this qubit over here. Whereas if f of A was equal to 1, so you'll get 1 parity 0, 1, 1 parity 1, which is equal to 0 over here. So you get 1 minus 0 as the state of this additional storage qubit, conditioned on the fact that f of A was equal to 1. These two equations then can be concisely summed together, or represented together via this. So you just note that essentially you have to just control this minus sign based on the value of f of A and just multiply it out with 0 minus 1. You can do your calculation backwards to verify that indeed this is the case. F of A equals 0, minus 1 to the 0. So that's plus 1. You get 0 minus 1 back, minus 1 to the 1. You get a minus 1 sign out. So you get 1 minus 0. So that works out. So what happened now? This computation over here where we had defined F to be computed and being stored into this additional storage for the purpose of implementing the circuit in a reversible manner, has now found its way back by basically saying, in the sense that this additional storage, you now note, is actually exactly in the state that it started out with. And the value f of a of the function that I wanted to compute, the actual value that I wanted to compute, has been stored in the phase of the state, not in the state itself, but rather the sign in front of it actually has the information about f of a. And that's cool. So now, because the reason being, now you can take this additional storage and kind of throw it away. It's no longer needed because your computation still, your value is in the phase over here. And here's kind of the key big picture intuition about how many of quantum algorithms work. This has already happened. And if you expand out the computations of the teleportation protocol about the superdense coding protocol, that quantum algorithms work by utilizing the fact that rather than the convex combination of probability vectors that we had for classical randomized information, in quantum information, you had these vectors now summed up via amplitudes. These amplitudes could potentially have negative signs in front of them. And just like we recall from high school physics, that waves have constructive interference and destructive interference. That's exactly what's going to happen over here. You get you get amplitudes over here where the signs will get flipped in terms of positive or negative. And the goal of quantum computing is to figure out, or quantum algorithm is to figure out a unitary that allows you to perform constructive interference for the specific states that correspond to the right answer, and destructive interference correspondingly for states that give you the wrong answer. And hence, you are amplifying essentially the probability with which you'll get the right answer. If you can amplify the amplitude exactly such that the probability value is to 1, you've got a zero error algorithm. If you can amplify it high enough, you get an algorithm that works with high probability, and so on and so forth. And that all kind of is already kind of evident over here from the phase kickback trick, where you note that the information that I wanted to compute has been stored in the sign in front of the state. All right. So this definition that I had in over this slide over here, where the information is being stored in this additional storage, via the phase kickback trick, that same information is now showing up over here in the phase. And that's something that will be used in multiple quantum algorithms that we'll see tomorrow. All right. We'll see just one example today, though. A simple example. It's kind of like a toy example again. And it's kind of a special case of Grover's algorithm that we'll see in Thursday. Unfortunately, this simple example doesn't generalize, and I'll leave that as an example for you to work out. But first, let's actually do this itself. So the setup over here is that we are working with a class of kind of algorithm that's known as Oracle or query complexity algorithms. If you've been doing algorithms, or if you have any prior exposure to programming or algorithms, you recall the standard we think about complexity of algorithms, we'll have more to talk about that soon, is by figuring out, well, how much work does my algorithm do in terms of time or space? And so I quantify the amount of memory or the amount of time my algorithm uses. In query complexity, as some people have already been identifying these sub as oracles, I will just count the number of times I make a call to this oracle. The number of times I call this oracle will be called my oracle complexity or query complexity. So in this simple example, the idea is I know that I have a set of 4 possible functions. These are kind of almost the standard basis functions for 2 bits, right? So I have a 2-bit input, and my 4 functions are the cases where the first function will just be 1 on input 0, 0. The second function will only be 1 on input 0, 1, and so on and so forth. So I don't even have all possible 2-bit functions. Oracle, for the lack of a better word, think of for us as just a logical gate that I will not, for the moment, be interested in unpacking. I just know that there's a certain gate, just like I've defined this over here, that will work according to this definition. How do I actually construct it will naturally depend on what F is. But for the purpose of Oracle query complexity, at the moment, I won't actually worry about opening up this oracle. We'll have more to talk about it in a couple of sessions. But for our current purpose, when we talk about query complexity, imagine that someone gives us this B sub f. So when that person constructed that B sub f, it already encoded this information about f. So we don't know what specific f is being encoded in the B sub f that we've been given. For a particular problem, we might have an additional promise. So for example, in this case, we are promised that this B sub f, this oracle, which is nothing more other than a quantum gate, circuit gate, this B sub f, the f being represented will have been chosen to be one of these 4 possible functions. Recall from yesterday, the number of possible functions on 2 bits are going to be 2 to the 2 to the 2. Here we have restricted that space, and whenever you restrict the set of input possibilities in this way, you say you are kind of considering a promise problem. So I'm promised that the function f will be one of these 4 functions. I don't know which one though. And the task for you is to figure out which f is being encoded by this B sub f. The only thing that you can do is to query this B sub f, which means you give it a certain input and it will give you the output as defined by us, and you'll figure out what you get. If we get, so the question on Zoom, if we get rid of the state B, i.e. no. So the interesting thing, Omar, about phase kickback is exactly once you get the output over here, you can throw this minus state in the garbage and everything is fine, because note that this thing is not entangled with this additional storage. You just need to be playing around with this state. So in this particular example, the way we have defined B sub f via phase kickback, you don't really need this additional storage after implementation of B sub f. Okay, so after B sub f has been implemented, you can really throw this in the garbage. And so sometimes in some quantum circuit representation, you'll see this like going like an arrow. Some person who had too much time on it might actually even design a dustbin in front of it. All right. Okay. Back to our task at hand. I want to come up with a quantum algorithm that will figure out which of these 4 functions is being encoded by B sub f. Step back and think about the classical problem. Same approach, but now I don't have quantum states. I'll be just working with classical information. I've got a circuit that will take 2 bits as input, x and y. These 2 bits. If you feed it 0, 0, if the function f was this one, then out will come 1, 1. But on all the other 3 functions, well, out will come 0. So if I got lucky and f was this one, and I input 0, 0, I get 1, and I know, hey, f0, 0 was the f being encoded. But if I don't know if the output was 0 over here, then I'm again stuck that it could have been this function, it could have been this function, it could have been this function. So in the worst case scenario, I will need to make 3 queries to B sub f in the classical case, right? So let's say the function f was indeed f0, 0. I input 1, 1, outcome 0. I don't know what function it is. I input 1, 0. I still don't know which function it is. I input 0, 1, outcome 0. Now, when I get 3 zeros on all the 3 inputs that I've done so far, I know for sure the 4th input is going to evaluate 2 or 1, because I know that the 4 possible functions being encoded by B sub f are these 4. So hopefully you're convinced that in the classical case, if I have to distinguish between which of these 4 f's is being implemented by B sub f, I'll need to make 3 oracle calls to B sub f. Let's see how this is doable via just a single oracle call in the quantum case. What's the quantum algorithm? These 2 bits represent my input bits over here. I've got my additional storage initialized to 1, apply the Hadamard. So over here, it's going to be in the minus state, exactly as a setup for phase kickback, B sub f, as we've been defining previously. So nothing special going on over here, apart from the fact that I've got the 0, 0 applied, Hadamard being applied all over here. I know what's happening over here. I get the minus state, and quick kind of calculation. 0, apply Hadamard, we know it gives the plus state. Well, now I've got 2 states. I will apply, well, let's write it out explicitly. Hadamard, tensor Hadamard on 0, 0. Well, I could write it out as plus, plus, but the nicer way to think about it as well is, well, what happens when you expand out plus, plus? So you'll get 0, 0 plus 0, 1 plus 1, 0 plus 1, 1. And so the nice way of thinking about it is that after applying n-fold Hadamard to n qubits initialized in the 0 state, you get the state to be, well, in this case, they're just 2 qubits, and you get the same, right? So you get a uniform superposition of all the possible bit strings. If you only had 2 qubits, then you only have these 4 possibilities. And so usually when you see in a popular science description that quantum algorithms work by considering all possibilities in quote unquote parallel, it's essentially referring to this key step that's a staple of pretty much every quantum algorithm that I know. Hey, take your initial state, perform Hadamard's on them, such that you get a uniform superposition of all input possibilities. In this case, now we continue on to apply B sub f over here. So what's happening, that this B sub f gets applied on this entire superposition. So it's being evaluated on all of the 4 input possibilities, because all the possibilities are in superposition, right? So at time step t sub 1, you started out with psi 1 being this state. We just verified this calculation in the previous slide, plus this one from the minus state. Psi 2, after application of B sub f, well, that's just going to be determined by phase kickback that we've defined previously. What is phase kickback? Well, we just noted it will give you this phase sign in front of each state, right? So in case of 0, 0, I get -1 to the f0, 0 in front of it. In case of 0, 1, same thing with the f of 0, 1 in front of it, so on and so forth. And you already hopefully see kind of the interesting thing that's going to happen here now, right? Recall the 4 functions were such that they took each function became 1 on exactly 1 value. So that means in this superposition, depending on whichever f has been selected, I'll get a minus sign in front of exactly 1 of these states. In particular, if f was 0, 0, then I'll get the minus sign in front of 0, 0 and positive everywhere else, plus everywhere else. In case of 0, 1, minus sign here, here, here. Quick verification I leave up to you. These 4 states are in fact orthogonal states. Bit of linear algebra review. If these are orthogonal states, for sure I am able to distinguish between them because they are orthogonal. But if you're not convinced about that, exercise for you, figure out what transformation I need to apply over here, such that you will indeed get either 0, 0, 0, 1, 1, 0, or 1, 1 as output in each of the 4 unique possibilities. You don't necessarily have to do that because it's already enough to convince yourself of that over here, that these 4 states are in fact orthogonal states. So you're able to distinguish between these 4 states now. And so via a single oracle call to B sub f, I've been able to identify whether or not f was encoding f0, 0, 0, 1, 1, 0, or 1, 1. If you have to make separate oracles for each winning state, it won't be very fun. So we don't have to make Shakil, so that's exactly the point over here. We don't have to make a separate oracle call for each different state. Because of this initial step that we prepared the 2 input states in uniform superposition, when I apply B sub f over here, this state went from just a uniform superposition to still a superposition, but with this nice phase sign in front of them that has a minus, that will evaluate to minus depending on exactly 1 location, depending on which f it was. Now, perhaps you're referring to the fact that actually designing the insides of this B sub f are going to be complicated or not. We'll come to that later. But for the moment, if I imagine someone does indeed give me a B sub f, and I don't know which f is being encoded, but it is one of these 4, then indeed this evolution does work out as given. So Artem, interestingly enough, the exact same approach will not work out if you now say consider the same problem, but now over 3 bits. And I welcome you, you to kind of verify that. The thing that goes wrong is that in the 2 bits case, you got these kind of 4 states that are going to be orthogonal to each other. Well, why does that work out? Well, you can kind of see that there are 2 cases where you get kind of a minus sign contribution in the inner product, 2 cases where you get a plus sign whenever you take the inner product between any pair of these states. And so the inner product is 0. But if you take now the states that will be over 3 qubits, so you'll have 8 states in the superposition, but you'll still have minus sign in front of exactly just 1 part of it, right? So you get a minus sign here, let's say, you get a minus sign here, but then there will be 6 additional states with all of them having a plus sign. So when you do the inner product, you verify that they are not orthogonal, and so it doesn't work out when you generalize it. but we will work on a generalization of this algorithm, which is exactly Grover's algorithm. But the result is not as good in the sense that Grover's algorithm doesn't guarantee that we get the result out by just one oracle call. We'll see what the complexity is there. Any questions here? All right. So we've done a toy algorithm today. We haven't really built a full kind of generalized algorithm. We'll start doing that with Deutsch's algorithm tomorrow. I'll stop with the quantum basics, what AB means. So I can do a quick review what AB means. So A is just in fact, rather, let's quickly go back and say, we had defined that 0 and 1 refer to these basis vectors. And so that's kind of pretty much a starting point of the representation, ket representation in quantum states. I welcome you to look at the QBronze Jupyter notebooks. They'll kind of lead you through this notation in a much more gradual fashion, right? So when I say A over here, I'm thinking about A as either taking the value 0 or is A taking the value 1. Use this fact to now know that, hey, this is just one of these two vectors. All right. Elisa, good question. What happens if you don't restrict the space? You don't have promise problems? Well, relatively less is known, right? So for quantum algorithms where you have certain promises applied, we have some well-known results. Those are exactly the algorithms that we'll do tomorrow, and that led up to Shor's algorithm. But if you have no promise, then the general belief is that you won't necessarily get the kind of speed ups in general that kind of we think Shor gives. But that's unproven territory. And that's exactly a nice kind of way to lead into our discussion on kind of computer science basics now. So when and where do we expect quantum algorithms to be successful? In fact, there was a discussion on Discord as well regarding why do we expect quantum algorithms to be better than classical algorithms? Short answer, Shor's algorithm. Long answer, slightly longer answer. Let's work through the next few slides. So the slides here are taken from Scott Harrison's multiple wonderful lectures and presentations on complexity theory. We'll just do a subset of it. And I'll try to motivate some of the notation coming from complexity theory that's useful to talk about analyzing quantum algorithms and whether or not there is a quantum advantage or not. For sure, we won't be able to be exhaustive. You can just look at Scott's lecture notes or some other lecture notes. I can share them on Discord. All right, so we are putting on a different cap now. We are thinking about just from classical computer science, think about how do we measure complexity of algorithms. And so that will require a little bit of history lesson. And the key history lesson that we want to start out with is the Church-Turing thesis. Kind of like high school physics, Newton's laws of motion, foundation of your introduction to physics. Somewhat similarly, computer science, the foundational bedrock is the Church-Turing thesis. Nearly 100 years old. And what's that saying is, so the history, in fact, is slightly longer than 100 years, older than 100 years, right? So year 1900, David Hilbert says in his address to Congress of Mathematicians, set of problems that mathematicians should focus on for the next century. Among them is essentially his notion of what a modern day algorithm is. A couple of decades later, Turing and Church formalize that notion in terms of saying, hey, if you want to compute something, then essentially that means compute it on a Turing machine. And we don't necessarily need to go into the theoretical definition of a Turing machine is. When I say a Turing machine today, you can think of the computational laptop, desktop, phone, whatever you've got in front of you, all of them being equivalent in terms of their computational power. Now, naturally, you might say, hey, wait a minute, me working on my laptop today, me working on my laptop 6 years ago, there's a difference in what I can do on each of them. And I'll kind of try to clarify briefly, what do I mean by their equivalent? As Scott Harrison likes to say, that this notion of Church-Turing thesis has a lemma, which is the existence of software industry. Why? Because with the Church-Turing thesis, you got this notion that I don't really have to focus on designing new or different kinds of hardware. I can have one fixed hardware design and just worry about the software that runs on it, the logic that dictates how that hardware will function. And so that's coming from this notion that, hey, I just need one hardware design. That's the consequence of the Church-Turing thesis. Well, what is it really saying? That any computational device is going to be universal, i.e. anything can be computed, that can be computed on it if it allows me to do kind of these basic tasks. Nice part, that the amount of memory I have is unbounded. So unbounded here is different than infinite. Unbounded here basically means that I don't necessarily fix a finite amount of memory, but if you say that, hey, I want to solve a problem with input size n, I will require some f of n amount of memory. You can guarantee that your computational device will have that f of n amount of memory. So in that sense, unbounded. I can read that memory, I can write to that memory, I can have looping constructs, conditionals, and that's essentially about it. If your computational model allows you to perform these operations, your computational model is universal. And obviously the laptops and the devices in front of you allow those procedures, hence they are universal. And that was exactly the identification that was useful nearly 100 years ago, right? So you had this notion of Turing machines, you had programs written in Lisp relatively later, you had this notion of cellular automata, you had notions of, so this is kind of cellular automata playing convex game of life. You could have lambda calculus or any other notion since then that people have come up with. All of them are equivalent. If you know to program in one of the models, you know how to program all of them. Just like today, if you know one programming language in principle, you can program in other programming languages as well, syntax issues aside, right? So the notion of Turing machines led to this notion of Church-Turing thesis, i.e. all models of computation that are sufficiently powerful are all equivalent. So that led to this notion of computable versus uncomputable. Turing in his original paper already identified, when he defined this notion of Turing machine, he also defined, hey, here are a class of problems, or here's a problem that my machine will not be able to solve. That was identified as a halting problem. In modern day terms, the halting problem is when I tell my Windows 10 machine to open up a certain program and I see the R class, how long do I have to wait before I figure out that, well, it's never opening up, right? So how do I know when I run a program that that program will actually halt, right? So this is kind of perhaps a multi-billion-dollar problem that someone might want to solve. Any software company that would like to be able to debug their code will love to have this possibility. Turing, right, pretty much at the inception and conception of computer science says that, hey, such a problem cannot be solved by computers. At the same time, lots of problems are indeed decidable by computers, as we know. However, this also leads to a nice connection with the physics perspective, right? So the modern way of thinking about Church-Turing thesis is not necessarily just about universality of computation, but it's how we treat it, right? So today, scientists would use simulations of physical models as a key way to do more science, learn more about science, right? So we take it almost as a given that if you've got any kind of physical model, you can simulate that model on your computer. And the idea then of the Church-Turing thesis is that you can really do that simulation to any amount of desired precision. So you've got kind of this physical flavor to quantum, to the Church-Turing thesis. Quantum computing is Turing complete. Some people would have earlier on liked to argue that it's more than, it's super Turing complete, but pretty much there's a consensus in the field today that no, it isn't. I'll talk about it soon. Right, so the Church-Turing thesis could be falsified. Tomorrow we identified a physical procedure in nature that solves the halting problem. It's another story about how you would get convinced that it's actually solving the halting problem. There's a wonderful paper by Michael Nielsen that I'll try to link on Discord later that identifies kind of this nice little tension that, well, there's nothing in quantum physics that says the halting problem is not, there couldn't exist a unitary procedure in nature that solves the halting problem. So, but computer science says that the halting problem is not decidable. So that then imposes this restriction that all unitaries that would imply solving the halting problem cannot be implemented. So you take an impossibility result from math, and that then is enforcing a no-go result on quantum mechanics, on physics. So that's kind of a nice opposite direction, which is interesting, right? So tertiary thesis essentially says that we can simulate reality. Well, in actual reality, 1950s, circa 1950s, computers actually start becoming available. You start designing programs, and you find out right at that time that just this notion of computability is not going to be enough, because you identify problems. Here's one example, identify real numbers for which this inequality is satisfied. And you realize that there are going to be problems that even though they are computable, you will have to wait longer than the lifetime of the universe to be able to get the answer from your computation device, i.e., your programs just take a long time, even though your problem is decidable, is computable. So the notion of computability is not enough. What you need to bring in is the notion of complexity. And this one picture kind of sums it up. Complexity theory, that, well, you could have a function that grows linearly, quadratically, exponentially. And the key distinction, high-grain distinction that we are doing is that computer scientists would say polynomial runtime good, exponential runtime bad, because exponentials are just not going to be sustainable, right? So if your runtime of the algorithm is growing exponentially, very soon for small sizes of n, the corresponding runtime will be so large that you'll have to wait till longer than the lifetime of the universe to get your algorithm to finish its computation. And that's in practice just as bad as not being able to compute, because even though in principle the problem is computable, but you'll have to wait longer than any person would be willing to wait to solve their problem, right? So this is the big kind of key principle for separation, that polynomial runtime is what you might expect physically to be doable, even though something like n to the 7, n to the 8 is not really going to be efficient. But exponential, anything like 2 to the n or worse, is not going to be sustainable. There's a nice story about this distinction between, or the notion that exponentials are really not sustainable, related to the invention of chess. You might have heard this story in multiple different ways. Wikipedia has a nice entry about them. The idea goes, some king is bored. The grand scholar or vizier comes in and says, hey, I've invented this game of chess that hope you like. The king really likes the game and asks the vizier to, or scholar or beggar to, ask for whatever reward they want. And the vizier, the beggar, just asks for a simple reward. They say, all right, you've got these 64 squares on the grid. Place 1 grain of rice on the first square. Place 2 grains of rice on the second. 4 on the third. 8 on the fourth, and so on and so forth. You get the idea. And so the king, who wasn't necessarily good at math, says, hey, wait a minute, that's just going to be a handful of rice. Give that to the beggar and be away with it. The royal granary kind of person comes along and says, hey, wait a minute, we don't have enough pieces of rice in the entire royal granary to satisfy this demand. And Wikipedia article states that the entire world production of rice even today is not sufficient to satisfy this demand. Why? Because this is an exponential growth. So even just going up to 2 to the 64 is really not possible physically. So really that's this kind of principle about this distinction behind why exponentials will be not considered to be sustainable or feasible. Side note, computer science will say polynomial good, but what if you have an algorithm of the size of runtime n to the 1,000, or you have an algorithm that's exponential, but with a base factor like this? So I won't get into this right now, but if you're interested in reading more about it, there is this blog maintained by Richard Lipton that talks about this notion of galactic algorithms, right? So polynomial algorithms with a really large constant power, or exponential algorithms with a very small base, and kind of they discuss about, well, why is it that most algorithms that we know don't actually fall in such a category, that they don't. So if you've got a polynomial algorithm in practice, it will have a small power. If you have an exponential algorithm, it will basically be something 2 to the power something rather than 1.000 or something like that, right? So, but there are some specific counterexamples they give, and they term as galactic algorithms. So this then this notion of asymptotics in terms of polynomial being good, exponential being bad, takes us from computability theory to complexity theory, where we are now interested in how efficiently can we do the computation. And that leads us to the definition of classes of problems. So this notation over here slight modern, so you don't know, I think, the star. So yesterday we had used this notation, so that would have meant all bit strings of length n. When you've got this 0,1 star, you can think of this as a clean closure. I'm identifying this as all strings of arbitrary length. So any possible binary string of arbitrary length will be included in this set. Whereas over here, you've got only strings of length n, whereas over here, you've got all possible binary strings. So any possible input you can give to a program, right? Okay, so the way we define then these problems is that you will receive an arbitrary input from all possible binary strings, and I want to be able to make the claim, hey, should this string be accepted or not? That's what it means to say, is X in L or not? Right, so L in computer science terms would be a language. You can think about it as a problem as well. Should I accept certain strings? Should I reject certain strings? When I'm considering, so note over here, I don't have any promise. I'm considering all possible inputs, and I have to do this binary classification. Some binary strings will get labeled as yes, they are in the language. All the remaining binary strings will get labeled as no, they are not in the language, right? And I define the first key complexity class, which is a class P. Think about it as basically the set of all problems for which I could run a deterministic algorithm on my modern computer, such that I will always correctly answer yes after a number of steps that are polynomially bounded in the input size, right? So if the runtime of my algorithm is polynomial in the input size, then the problem is in the class P for polynomial, right? And there are many interesting, useful problems that we know are in the class P. Every time you use Google Maps to tell you how do I get from here to here, you are solving connectivity problem. Primality testing a couple of decades ago shown to be in P that, hey, if you've got a number, is it a prime or not, can be done in polynomial time, different from factorization, right? Primality testing is just given a number, is it prime or not? Factorization is in the class NP, which does not stand for not polynomial, it stands for non-deterministic polynomial. Rather than going into the intuition about how do we think about non-determinism, this nice intuition is really very useful for thinking about the distinction between P versus NP. In P, we actually wanted to generate the solution. The algorithm told us after polynomial number of steps, yes or no. Here, there's a polynomial time algorithm that will recognize a given solution as valid or not. So the way to, and here's kind of a beautiful kind of contribution of CS in terms of distinction between determinism versus non-determinism. In non-deterministic polynomial time, the way I think about the algorithms is that they have the property that if you give me a candidate solution, I can verify that the solution is a valid solution or not in polynomial time. Case in point, for example, factorization. If you give me a number and you give me a list of factors, if they are not the correct factors of that number, there's an efficient way to verify that. I just multiply out that list of numbers and I check, hey, that's not equal to the number n. You gave me 15 and you told me 7 and 3, 7 times 3, which is easily doable because it's just multiplication. So I do find out via a quick multiplication procedure that, hey, 15 does not have factors 7 and 3. But if I gave you 5 and 3, then hey, yeah, 5 times 3 is 15, 5 and 3 are factors of 15. So factorization has this property that the solution can be recognized efficiently. And there are lots of interesting problems that are known to be in NP. And it's not just that they are interesting, it's that they come from a diverse field of interesting kind of pursuits. So logistics, finance, simulations, drug design, you name it. You take any kind of human endeavor and you'll figure out that there are interesting computational problems in that field that belong in the class NP. Unfortunately, though, there's this issue that many of those interesting problems now will come in this flavor that rather than just being in the class NP, they will be NP complete, i.e. they are the hardest problems in NP. At the same time, we believe that there are problems in the class NP that are not necessarily NP complete. So NP complete are the hardest problems in NP. If you can solve any one of them, you can solve all of them efficiently. We don't know though. That's exactly what this last line is telling us over here, that we don't know whether P is NP. We're coming to that soon. We know that the NP problems have this property that they can be recognized efficiently, but we don't know whether it will be able to find the solution efficiently. Now you take the set of problems and consider the hardest problems in them. What do I mean by the hardest problems? Intuitively, that if I have a solution to any one of the problems that's NP complete, I will be able to use that solution to solve any other problem in the class NP as well. So that allows me to really focus my algorithmic attention towards just one problem, let's say traveling salesman, and say, hey, can I solve traveling salesman efficiently? Because if I were able to, then I would have shown that all other problems in the class NP are also efficiently solvable. And it's interesting enough that the one example being provided from quantum computing for this interesting quantum advantage is this problem of factorization that is not known to be NP complete, even though it's an NP. And so that leads this kind of situation into lots of interesting rich structure. So yes, quantum computing does supply us with some interesting quantum advantage, but it doesn't go all the way to solve NP complete problems efficiently, we think. And so the expected worldview, right? So it could be tomorrow some smart people among you prove P equals NP. We strongly believe that's not the case. But the expected worldview is that at the lower level, we've got this class P that contains still lots of interesting problems that can be solved efficiently. But this P is just going to be a subset, is going to be potentially, we don't know. We think it's going to be a subset of this bigger class NP. And this bigger class NP contains the hardest problems in this class NP are labeled as NP complete. There can be harder problems as well that are labeled as NP hard. We don't need to worry about them at the moment. So these NP complete problems are the ones that are inside NP and are the hardest problems in NP. So if you want to solve the P versus NP problem, if you don't know about it, next slide, we're coming to it. You want to focus your attention on solving this NP complete problems in one way or the other. At the same time, there are these two at least interesting problems that we know are in the class NP, but we think they are not NP complete. And they are interesting for the purpose of cryptography and whatnot as well, right? So factoring being something that is close and dear to quantum computer scientists. Okay, so what's the P versus NP problem? We want to prove whether or not P and NP are the same classes. The Clay Institute gives a $1 million award for solving P versus NP, but really if you were able to solve P versus NP, you'll be able to use that algorithm or the impossibility proof to earn much more than just this $1 million. And the history of it dates back to a letter from Gödel to von Neumann. You can find it online. In fact, if you want all the gory details, there's this lovely review paper by Scott Aronson on P versus NP. You can read up all the fun details there. We are going beyond our scope for our current talk. So if P is indeed not equal to NP, how could we really think about improving our computational ability? That led to the notion of the extended Church-Turing thesis. The extended Church-Turing thesis basically said, as a strengthening of the Church-Turing thesis, the original Church-Turing thesis said all computational models are equivalent. The extended part of the Church-Turing thesis actually said that they are all equivalent in a feasible manner. That is, all different models of computation can be simulated by each other efficiently. And the counterexample, and the only known counterexample to that, is what we have in the form of quantum computing. The key argument came from Feynman. They said, all right, it seems, and this is where we connect now to yesterday's discussion as well, where we noted any separable entangled state can be efficiently simulated by a classical computer, but obviously all the interesting states in quantum computing won't be separable. So Feynman noted the fact that if you wanted to simulate quantum information or quantum mechanics on a classical computer, that seems like a hard problem to do. And so he turned the question around and said, well, what if our computer is quantum to begin with? That essentially led to the foundation of quantum computing. And that was, and I think also still remains, one of the key killer apps for quantum computing, right? Simulating physics in of itself, simulating quantum mechanics on a quantum computer. If you're able to do that, you'll be able to open or unlock new ways of doing science that we at the moment don't have. Quantum sensing, for example, just being kind of the first step towards it. For sure, to get the computer science people interested and more involved, shows result that, hey, you can do factorization efficiently on a quantum computer kind of was critical. But from the physicist's perspective, this Feynman's question already is kind of a killer app. Now, for Shore's perspective, remember this kind of observation that factoring is not known to be NP complete. So tomorrow, it could be possible that someone shows an efficient classical algorithm for factorization. So the speed up for factorization that quantum computing gives, apparently, might go away if that happens. Lots of smart people have tried doing that and have failed for better part of more than half a century. Not happening, but we can't say for sure. However, even if that happens, this killer app from Feynman's side still remains. If I want to simulate quantum mechanics, build a quantum computer. Much of the discussion today regarding verifying this experimental devices built by Google and other companies goes back to the fact, hey, can I do kind of simulations of interesting quantum systems on them? To begin with, that would be a nice kind of application of quantum computing towards a practical problem. So to conclude with, though, the real world situation in complexity theory in relation to quantum computing is much more nuanced and interesting than someone might have thought. Why? Because here's this new little class that I've added in based on the previous slide. So we looked at P, we looked at NP, we looked at NP complete. I already mentioned it seems like quantum computers won't be able to solve NP complete problems in polynomial time. So we won't be able to get all of NP within quantum computing. Yet at the same time, factoring is efficiently doable by quantum computing. So that's in the class what's called BQP. Now the classical version of BQP is actually BPP and not NP. You can look it up on Complexity Zoo. So Complexity Zoo is a great, wonderful resource for getting to know all about these different complexity classes. Just Google this up. Quick note, why is this quantum situation weird? So Scott's drawn this kind of weird little region where he puts BQP outside of all of NP. If you've been following along all this conversation, what have we discussed that allows us to do this? Why is BQP outside of NP? Anyone on this call? So BQP are the algorithms, are problems for which there exists an algorithm on a quantum computer that could solve would solve the problem in polynomial time with some bounded error. So Shore's algorithm allows us to get factoring inside BQP. Scott's claiming over here is that BQP is actually also outside of NP as well. Why? And with that, we'll finish. So the statement for BQP won't relate to any NP problem, right? So we are outside of NP over here. So this is exactly the problem that we encounter with all our modern day applications or potential applications of quantum computer, right? So Google says they've built a quantum computer. How do I verify that they've built a quantum computer? If it were possible to efficiently verify the output of a quantum computer, that problem would be inside NP. But as we discussed yesterday, there is no efficient simulation of a quantum computer. So if someone has run what they're claiming is a quantum computer to do some computation, to verify or not whether that was an actual quantum computation is not known to be doable efficiently. So this structure that we said that the class NP had, that I can verify the solution efficiently, the problem of verifying whether a given computation was a valid, interesting quantum computation does not seem to have the structure of NP. And so BQP potentially has problems that lie outside of NP as well. So verification of a quantum computer essentially being such a problem. All right. And so that leads us to this interesting kind of current expected state of the field, where we don't know whether factoring will become NP complete, or whether P and NP will become equal or not, or what's the relation to BQP, not to speak of what's happening with BPP in relation to BQP. And I've just made it really messy. All right, questions, issues, concerns, sarcastic remarks?
Thank you, JIBRAN. And the official time of the session is over, but feel free to stay on for a little more if there are more questions.
Sure. Yeah.
Because this is
so we're done for the discussion.
Yeah.
Is it just a claim? So the claim that BQP is outside of NP. So it's kind of the same thing as, well, we don't really have a proof, but we strongly believe that BQP will be outside of NP because quantum verification of a quantum algorithm in general could not be done efficiently. But my recollection is that that would be exactly the argument for making the case that BQP is outside of NP. Right, so you could have some specific implementations for which the verification could be done, but in general, for any given quantum computer, do the verification efficiently? We don't know. From the intuition. Is it because of non-determinism? So yeah, not non-determinism, right? So anything related to non-determinism is just kind of within the class NP. Once we are outside of the class NP, then we're talking about some property that has nothing to do with non-determinism, that has some other issue. And so when we are saying that, hey, yes, there's a problem that's inside BQP, but not in NP, it means that there's a problem that a quantum computer will be able to solve efficiently, but the solution cannot even be recognized efficiently via an NP machine and or via polynomial time machine. And so that's exactly what we currently understand is the state of the art in terms of verifying whether a certain computation was actually a quantum computation. Right? So the best known algorithms in general would be really just simulation of the quantum algorithm itself, which will happen on a classical computer in exponential time. Whereas if you had a quantum computer, then just running the algorithm in polynomial time would be the BQP algorithm for it. So quantum computation would render other advantageous domains of computation rather than speedups of classical ones. So quantum computation would render other advantageous domains of computation rather than speedups of classical ones. So yeah, so we don't necessarily understand the entire set of class of problems on which we will get a quantum advantage. That's one of the big open problems from a computer science perspective, right? So side note again, with the advent of kind of NISQ devices, the perspective of analyzing NISQ devices is also slightly different, right? So there you don't necessarily take this complexity theoretic approach. There you rather say you take kind of the more hacking approach, right? So if I've got an algorithm, if I've got a program that solves a problem in 1 month, and if I've got a problem that halves it and runs it in 15 days, or that's kind of very crucial key practical difference, right? So with NISQ devices, you're not necessarily always looking for a complexity theoretic separation, but rather it would be sufficient for you to say, hey, the best known classical algorithms work with this complexity or take this much time. We've got an algorithm working on NISQ device that seems to work in less time, right? So that's what people are trying to do with NISQ devices, not necessarily get a complexity theoretic separation, but just get a separation that seems like in practice something that runs faster. So do we now have an idea of what the properties that problems under BQP have, but the problems and the NP don't? Simarth, I actually don't have a good answer for that question. I'm sure there must be something in other lecture notes that will give that intuition if that's known. We'll have some kind of related answers as we go along in kind of Grover's algorithm and whatnot. So the key kind of takeaway is that for all unstructured search, Grover's algorithm that we'll do in 2 days is one key quantum approach that does give a benefit, but it only gives a quadratic improvement. And it's provable that it's the optimal improvement that can be expected by an unstructured search. Now, whether there are other cases in which quantum can provide an advantage, there's a recent result by Zandri, which I haven't really had a chance to work through, that shows that yes, there could exist other cases in which a quantum advantage can also exist, but I don't really know the structure or the details over there. The purpose of phase kickback. So the purpose of phase kickback is really, it helps us in analyzing the quantum algorithm, where we have this computation of the classical function f. The result was stored in the additional storage, additional qubit, but via the phase kickback, we were able to make that information show up in the phase. And via showing up in the phase, now you know that we can play around with the amplitudes, as I mentioned, by constructive and destructive interference. And that directly influences the probability of what will be the measurement result. So via the phase kickback trick, it's just a mathematical trick, right? There's nothing different or that we're doing experimentally. The phase kickback is just a mathematical trick that helps us in analyzing the algorithm in terms of with what probability it gives what answer. And we'll see kind of the explicit implementation of that hopefully tomorrow. But even the simple example that we did for search kind of shows it. Via the phase kickback, we were able to evaluate the 4 different states and noted that those 4 different states are orthogonal. Right. How can we make sure that our algorithm has a lower complexity? Well, your question is, Osman, your question is essentially asking, how do I design efficient quantum algorithms? I don't have a good answer to that, right? So there are classes of problems that have a similar structure as Shor's algorithm, and they have been well studied, known as the abelian hidden subgroup class of problems, for which we know that already here's a quantum advantage. Grover is another case. And then there are a couple of more recent cases coming from boson sampling and HHL algorithm. So there are only like 4 or 5 different classes of quantum algorithms for which we know, right, here's a general technique for getting better complexity than classical cases. Much more needs to be done. BQP intersects with NP hard problems. So for sure, it won't go into NP because of the notion that we know that BQP doesn't contain all of NP. It won't really have an intersection with NP hard. Would be the expectation. Could not be a quantum system. Right. So NP, the class NP, uses this abstract notion of non-determinism, right? So even classically, you won't really be building a non-deterministic machine. It's just a mathematical abstraction that helps us in computational design of algorithms. David, excellent question. Quantum complexity in NISQ era. I think stuff like boson sampling and related stuff is exactly the place to get started reading up on quantum complexity in NISQ era. But as I mentioned, like, most of the discussion for NISQ algorithms has been kind of, hey, look, I implemented something that seems to work faster than anything classical. I'm sure there's kind of more state-of-the-art stuff that I'm not aware of at the moment. But yeah, the quantum complexity for the NISQ era definitely needs to be worked upon. Yep, Scott's notes on quantum complexity. Quantum systems not equal to quantum complexity. Other verification possible. Combining space and time complexity together. Sharma, you're essentially asking exactly one concept that's used in kind of analyzing today the complexity of quantum algorithms. So you talk about the volume, where you're thinking about a circuit, both in terms of its depth and width. And so that's essentially combining the space and time to essentially get the volume of quantum algorithms. So you can look at the discussion, I think, happening in the advanced quantum channel for stuff that combines space and complexity together. So the space and complexity parts are essentially, you take the circuit, you think about the depth, that will be essentially the time, and you think about the breadth or the width, and that's essentially going to be the space. And so people have for sure thought about combining space and complexity in that sense. BQP has a way to easily test a candidate solution. So BQP is the class of problems for which a quantum computer can solve the problem in polynomial time with some bounded error. So you don't necessarily think about in terms of recognition. You just, so this is kind of the generalization of classical randomized algorithms, which is different than non-determinism, right? So even classically, you have NP, and you then also have, well, BPP. I should actually make it slightly separate, more like this. Right, so you'll have BPP. I should have drawn it the other way because, well, and if you imagine this green region is not there, then BQP would have thought to be something perhaps like this, right?
All right, time to call it a day,
All right.
JIBRAN, and to
Sure.
continue tomorrow. This was
Yeah, so if I have
great.
left questions, I'll answer them on Discord later and post the notes that I mentioned later as well.
Can you give a brief overview which quizzes and exercises will be best for today?
Sure. Thank you.
From yesterday's lecture, the following quizzes were ready to do: QBronze 1, 2, and 3.
Yep.
Now
So QBronze 4, Entanglement and Basics of Quantum Protocols, is exactly what we did in the first half of the session today. We did do phase kickback, which is part of nickel as well, but I would recommend not getting started with that. Tomorrow we will do Deutsches and the phase kickback again. So that will allow us to do 1.1, 1.2, and 1.3 tomorrow. For today, you just get one additional QBronze, which is Entanglement and Basics of Quantum Protocols.
Wonderful. So the focus is on finishing that. And in the description, you also see which exercises belong to that part and the recordings from last year. Tomorrow, there will be a mentoring session 1.5 hours before the session starts. For everyone who has more questions, this can also be about the basics of quantum mechanics, Qiskit. You can ask all your questions there. This will be announced on Discord very soon. A similar mentor session will take place on Friday morning. Well, Friday morning in my time, 1.5 hours before the regular session start, and on Sunday. Looking forward to seeing you all tomorrow again. Tomorrow we will start with quantum sensing for biomedical applications, a really exciting talk, and then we will take it further with QKD and with JIBRAN on quantum algorithms and programming. Thank you all very much, and we will be in touch on Discord.